Okay, good afternoon. Let's get going. Let's get started. Apologies for the delay. I think we lost about 5 minutes. But today we're just going to wrap up chapter 3 op amps and then move on to chapter 4 if time permits. One of the questions being asked is when can we expect quizzes to be graded? So that's kind of on me. I was delayed in posting the quiz solutions to the grader. So the grader has them earlier this week and they should be getting those done. I just I've taken no, it's not about just being. So all right, let's switch over to the class notebook. Sorry, what? Well, I could cancel the final, but then you'll all have zeros on there. So not technically canceled. All right. Inverting amplifier and then non-inverting. Okay. So we looked at a lot of circuits and a lot of analysis using the inverting configuration. Let's look at a couple of circuits with the non-inverting configuration. I hope several of you have finished, well, not finished, but at least gotten a head start on the homework. I moved it to Friday, right? I think I moved it to Friday or Saturday. When did I move it to? Okay. All right, non-inverting configuration. It's rather straightforward. The basic rules still apply. The first thing we check is whether there is what kind of feedback is present in the circuit, right? So negative feedback is present. We can see that the output is fed back into the input of the inverting terminal. And so negative feedback exists, right? So negative feedback exists. And we can apply our virtual short concept, meaning II and VI is equal to 0, or the differential input going into the op amp is equal to 0. V in is the voltage that is going into the non-inverting terminal, right? Going into the non-inverting terminal. So the differential voltage VI, that will be pushed to 0 because of the output coming in, right? Output going into the inverting terminal. So VI is being pushed towards 0. II is also 0. So I can write V in would be equal to V1. That is the voltage across the resistor R1 and being fed back into that inverting terminal. Okay. We are saying the difference between the two terminals would be equal to 0. That would mean that the voltage at both points should be exactly the same. So at that point, for my analysis purposes, I can say that V in would be equal to V1. Now, I can write V1 by applying KVL in this loop. If I apply KVL in that loop, I can see output and feedback loop looks like this. I have RL, I have R2, and I have R1. And of course, this end is connected to ground. VO is measured across that load resistance. So if I apply KVL, I can see that the voltage here, well, I don't actually need to apply KVL. You can see it's in parallel, has the same voltage. So VO is being dropped across R1 and R2. Can you all see where this is going? One person does. And so I can write the equation for V1 by using voltage division. So VO times R1 or R1 plus R2. And then you take that equation V1, plug it in here, rearrange the terms V in and V out to obtain the gain expression. And so when I plug that in, obtain V in is equal to VO times R1 plus R2. Oh, R1 over R1 plus R2. So V out over V in, you take it all on the other side. I get R1 plus R2 over R1. Separate it out, reduce it. I get 1 plus R2 over R1. Non-inverting amplifier, so there is no minus in there. It simply is 1 plus R2 over R1. So gain AV for a non-inverting amplifier is 1 plus R2 over R1. And in this, yes.
Is there any configuration of a non-inverting op-amp that gives you a gain less than 1, or are you always going to have that R1 over R1?
I was going to say, for this configuration of the circuit, you will always have gain that is higher than 1. Always. So if we plug in R2 is equal to 0, it'll be 1 plus 0, just 1. Or if you just simply take the output and feed it back into the input without any resistance, that'd simply be gain of 1. It'll still be a unity gain amplifier. Right? That's similar to the voltage follower. But there are different configurations, as we saw in the inverting amplifier configuration. There you could actually change the circuit design, and it may theoretically be possible to obtain a gain of less than 1. Now, for the, let's see, where is the, okay. I is equal to 0, input current is equal to 0. So if I wanted to calculate input impedance, R is equal to V over I. Even if V is very, very small, if I is 0, theoretically my input impedance would be infinite, right? V over R, V over I. So non-inverting amplifiers have a very high input impedance. Similar to an op-amp inherent property of high input impedance, a non-inverting amplifier will have very high input impedance. Compared to an inverting amplifier, where the input's actually going into the inverting terminal. So we calculate the input impedance for an inverting amplifier as V over I. And so that would give us R1, the input resistance of the inverting amplifier. Non-inverting amplifier has infinite input impedance. And the output equation VO does not depend on RL. Okay, it does not depend on RL. There is no mention of RL anywhere in that equation. So since it does not depend on RL, output impedance is theoretically very, very low. Theoretically, it is 0. Okay, so again, fulfilling one of the criteria of these kind of instrumentation amplifiers, meaning have very high input impedance and very low output impedance. All right. So in your homework, the non-inverting portion asks, there are, first is fundamentals. Second one is also fundamental about gain, high input impedance, low output impedance. That's actually the question being asked in the homework. So you already have the answer if you've already looked at it. And then the third is basically this problem. So before I do this problem, does anyone have any questions? Any questions? Yes.
So is the output impedance of this op-amp the same as your input impedance of like whatever you put the op-amp?
No, no, that would be completely different. So cascading a circuit, which happens, actually, there's an example right now in the last slide where you cascade it. It's completely independent. The reason we want very low output impedance is so that it doesn't load the next circuit, and it provides as much current as possible to the next next cascading circuit. Any questions? Any other questions? Okay. So problem 13.21. Take a look at this. What kind of circuit is it? It's a summing amplifier, non-inverting. So it is all of those things. It's a non-inverting summing amplifier. So we looked at an inverting summing amplifier. This is the last problem on the homework. Yes. No, the plus and a minus are flipped. So it's plus here, minus here. So non-inverting input is going in the non-inverting terminal. So non-inverting summing amplifier. And then did I understand your question correctly? Okay. Oh no, that is for feedback. So if the output, so it's a good point. If the output goes into the positive terminal, then it's positive feedback. Then the then the op amp is immediately driven into saturation. Saturation would be basically whatever the power supply we're applying. So positive feedback is not going to cancel out the input. It will simply reinforce the input and it drives it into saturation. We use it for like oscillators and other different kinds of applications. We're not looking at those at all. All of the circuits that we look in this class is all negative feedback. So negative feedback means the output goes into the negative terminal, and then the input can go either in the plus or in the minus. If the input goes into the negative terminal, then it's inverting amplifier. If the input goes into the positive terminal, it's a non-inverting amplifier. Yes.
So if we have positive
kind of, but rather than unstable, it drives it into saturation. Yeah, it kind of oscillates. So depending on the input signals, it oscillates between the positive voltage rail and the negative voltage rail. Not really. It depends on what we want to do with it. Again, if you want it to oscillate, we want an oscillator like frequency generator, then we want it to like go up and down, up and down, up and down. So you could say it's unstable, but it's a desirable because that is what we want in that sense. There are actual circuits that we use. So earliest is like we take these kind of circuits, and there is a classification of circuits that's called multivibrators. And so we have astable multivibrators, which does not have a stable state. That's desirable because we wanted to keep switching between two states. So an application of that was like, flashing lights, where you want lights to flash on and off. Let's say you have a set of green lights and a set of red lights that you want to turn on and off alternately. Then one state on, one state off. Red, green, red, green, red, green, keeps flashing. Then there's like monostable, and monostable means only one stable state. Bistable, which has two stable states, and well, so on and so forth. But anyway, astable, but it's on purpose. We want it, and the application would be oscillator. Oscillates between the positive and the negative voltage supply rails. Anyway, coming back here. So what do you think the output of this output equation of the circuit should look like? Rather than me beginning the solution, let me ask you. It's a non-inverting amplifier, right? So V out should have, what should it have? A gain of 1 plus R2 over R1. And we established it is a summing amplifier. So what is the input signal? Yes, but it's a summing amplifier. So it should be the sum of the two. Make sense? It's a summing non-inverting amplifier. So non-inverting, the gain should be 1 plus R2 or R1. That's in the negative feedback path. And then it's a summing amplifier. So to sum up all the inputs. If it's 2 inputs, VA plus VB. If it's 3 inputs, VA plus VB plus VC. 4 inputs, add up all 4 of those together. Conditionally, of course, that these resistors should all be the same. If you remember the inverting summing amplifier, we said that the resistors in the input path have to have the same values. Otherwise, it'll be a multiplication factor. So your output should look something like this. The derivation is not too onerous. It's rather straightforward. Let's call this current as IA, this current as IB. Right? You have 2 currents going in. Now, same principle applies. Negative feedback is there. So the differential input voltage going in is equal to 0. The input current going in is also 0. So II is 0 and VI is also 0. So I can apply KCL at the non-inverting terminal, and I can write IA plus IB is equal to 0. So this is from KCL at non-inverting input or non-inverting terminal, right? KCL. And that is all most op-amp analysis is. You do apply KCL, KVL, depending on what we need at the output. So now we need an expression for V out. So we need V out or V in somewhere, right? So let's take the output voltage. V out is going from here to here. Similar to the analysis, we can write an expression for VR1 in terms of V out. I can write VR1 from voltage division as V out times R1 or R1 plus R2, right? Voltage division. Now from the constraints, similar to the previous circuit, what did we say? The differential input voltage because of negative feedback is equal to 0 because the input terminal is being forced, the output is being fed back into the input, and then the differential voltage is being forced to 0. And we say both terminals have the same voltage. So if the inverting terminal has VR1, then the non-inverting terminal also has a voltage equal to VR1. All right, makes sense based on the constraints. And since the non-inverting terminal is at VR1, I can describe IA as VA minus VR1 divided by RA, and IB as VB minus VR1 divided by RB. And that's it really. Yes. So it's just VA. VA. It's basically the either side of the resistor, the node voltages on either side of those resistances. So VA minus VR1 divided by RA and VB minus VR1 divided by RB. And that's all we need. We take all of these and we plug it into this equation right here. IA plus IB is equal to 0. So you plug in values of IA and IB in there. Then you plug in VR1 in here and in here. And these two should plug in over there. Rearrange the terms and you should be able to write an expression for VO over V in or V out over V in. And you should obtain this expression that is up at the top. And of course, this is conditionally based on, let me write it at the top, if RA is equal to RB. If RA is equal to RB. Yes. Yes. Well, it will still be summing it up, except if RA is not equal to RB, then it'll be like a product. So let me see if I can remember the equation. It is VA times RB plus VB times RA divided by, I think it's RA, RB, or RA plus R. Can't remember for sure, but it's RA plus RB or something. And then it cancels out, and then you just get VA plus VB. The denominator, I think, is R. I can't remember from the top of my head right now, but when you plug these in, R1, right, IA, IB, and then you plug it into this equation, and you add it up. So VR1 is right here. We take this expression for VR1, you plug it in here and in here, then this plus this equal to 0. You reduce the expression, you should get 1 plus R2 over R1 times this quantity right here. If RA and RB are equal, then they cancel out. All you're left with is VA plus VB. Yeah, it'll still sum it up. So if RA and RB are not equal, it's still summing it up, except there is a multiplication factor that is involved. Yeah, it's weighted sum of weights or something. Yeah. All right, questions? No, I filed a ticket. They fixed it.
Oh, nice.
Apparently, it was an easy fix. Who knows? Because I tried it and it never worked. Yes. No, not really. In the homework, I think it's just asking for the derivation. So it's not, you're not asked to solve on the homework problems. Yeah, your answer would need to have RA and RB. So I think I've already given you more than enough information. So again, as a suggestion, while this material is fresh, if you have not yet attempted the homework, you should go ahead and do it sometime today itself. Okay. Yeah, some of you have already finished it. So, all right. Any other questions?
So, Professor,
Yes.
so that final GA or ERA, that's like the A plus BB, the equation, no?
Yes, IA plus IB. Yes. That's where we get the equation from. Yes.
Oh, no, I mean, because when you put B not equals I1 plus R2 1 EA plus BB, then the B plus BB is going to be that of.
What do you mean that? That's the final equation.
Oh,
That's just the final equation that you would obtain. You're asking about this equation right here? Yeah, that's just the final equation that you would obtain for this circuit if RA was equal to RB. I just started with that just to show, well, just to explain the circuit. Yeah. So active filters. Active filters. I was going to ask what kind of filter is this, but already states it's low pass, right? So if you remember from 201, chapter 6, quick and easy analysis method, you replace the capacitor and inductor with, well, its functional equivalent, either an open circuit or a short circuit, depending on the frequency. So capacitor impedance is 1 over j omega c, meaning the impedance goes up when the frequency goes down. So when F tends towards 0, capacitor is an open circuit. When F tends towards infinity, capacitor behaves like a short circuit. All it means is for low frequencies, capacitor is open. For high frequencies, capacitor is a short. So we won't do any quantitative analysis, but I will do a short qualitative analysis. Okay. So analyze and redraw the circuit for F tending towards 0. Low frequencies. Low frequencies, what happens? Capacitor is replaced with an open circuit. What kind of circuit are we left with?
No, it's inverted.
And that's it. So at low frequencies, circuit behaves like a normal inverting amplifier, right? So low frequencies, normal inverting amplifier. What happens when F tends towards infinity? High frequencies. Capacitor is replaced with a short. So if capacitor becomes a short, what happens? Yep. Well, actually, rather than a voltage follower, because voltage follower, we feed it back. The input is given at the non-inverting terminal. Voltage follower, right? Give it in the non-inverting input, not in the inverting. Here, the output simply is fed back into the input, and negative feedback, the constraints still apply. So the differential input is being forced to 0. If your non-inverting terminal is connected to ground, your other terminal is also being forced to ground. So your output is being forced to 0 volts. Since your output is forced to 0 volts, you can essentially say that it is working as a low pass filter, because low frequencies are allowed to pass through, high frequencies are blocked. So for low frequencies, you obtain V out as a multiple of V in. For high frequencies, V out tends towards 0. And you plot it with respect to frequency. Oh, V out with respect to frequency. You would obtain, well, F and V out will be low pass. So again, at low frequencies, capacitor behaves like an open circuit. So essentially, the circuit functions like a standard non-inverting amplifier. V out is equal to a multiple of V in, right? Multiple gain times V in. And at low frequencies, the output is forced towards 0. And so we can essentially say high frequencies are blocked and low frequencies are allowed to pass through. Yes. Because negative feedback, so output is being fed back into the negative terminal. So negative feedback, meaning our constraints apply. Input current going into the terminal is equal to 0. And the differential voltage between, the differential input between the two terminals is also forced to 0. So the differential voltage forced to 0, if you ground one of the terminals, the other terminal is also being forced to virtual ground. So that is an active low pass filter. The reason we say it's active is because we can actually provide a gain to our components if we wanted to. To our signal if we wanted to. And that in real life as an application for graphic equalizers, where it says like, bass boost. If you're doing a bass boost in your audio signal, that is what you're doing. You're providing a gain to the low frequency so you can hear more of the thumping sounds. Right? Graphic equalizer. uses active filters like these. This active filter providing a gain to the signal that's coming in while it's blocking out the other signals. So it blocks out the other signals while it's boosting the frequencies that we want. Yes. So you could be changing the value of the resistance. So old style boom boxes. I don't know if anyone has ever seen manual sliders. You've operated manual sliders, right? So the sliders are actually resistors. So they are, yeah, they're actually resistors. That's what's also, is there a dimmer switch in here? I don't see a dimmer switch, but sometimes you have dimmer switches, right? They just go up and down. Depending on what kind of circuitry it is, at its most basic, a dimmer switch could simply be a resistance. So, well, just going on a little bit of tangent. Anyone know what this is called? A variable resistor?
Potentiometer?
Well, I was going to say we call it pot. But potentiometer, yes. Pot. So if you ever hear electrical engineers say pot, that is what they mean, most likely. So a pot or a potentiometer is a variable resistor. It has 3 terminals. The outer 2 terminals are fixed. It's a fixed resistance. So if it's a 1K pot or a 10K pot, the outer 2 terminals is like a regular resistor. But if you move the slider, this can be like a rotary dial, or it could be like a rectangular, like a straight design. So graphic equalizers, if you on a boom box, they are like, they are these kind. And what we are doing is we are moving the slider back and forth along its pathway. So depending on the position, the resistance between any 2 of these nodes will change, right? So if this is 10, if R is 10K between A and B, and if C is in the midpoint, then RAC could be 5 kilo ohms. If you move it towards the left, RAC can take any value between 1K to 5K. Not 1K, sorry, 0 to 5K. 0 to 5K. Does that make sense? And so you have rotary dials too. So if you in your if you ever used a mixer, audio mixer has those circular dials. They do the exact same function. Audio mixer is like a DJ mixer. When you turn those dials like bass, treble, mid-range, all you're doing is you're taking the active filter gain and you're increasing the gain. Anyway, coming back from our tangent, let's look at the high pass filter. Again, we want to do quantitative analysis. We'll do qualitative, just describing. Capacitor at low frequency behaves like an open circuit. So if it's open circuit, Vin does not reach the op amp. Make sense? Vin does not reach the op amp. Allowed to pass. And at high frequencies, it behaves like a short circuit. Vin is connected to the op amp. As simple as that. And when it's connected, behaves like a inverting amplifier. Now, of course, as I said, the quantitative analysis, we do it for EE major classes. This active filters is essentially a chapter by itself. Yeah, we do. It depends on the education institution. If you're teaching Laplace transforms, yeah, then we could solve it using Laplace. Hence, that you see the S right there. So we'll ignore it for now. All right, let's see, 150. Let's get through and, oh, one other thing about this, especially for those of you who took the lab, what does the circuit remind you of? You already took this, you already finished this lab. Mathematical term. All right, let's jolt your memory. The current for a capacitor is C dV over dt. So voltage is what? 1 over C integral of the current. So what does this circuit remind you of? Output voltage, you're trying to find the voltage. Integrator. And y'all need some coffee. Or some food. So this exact same circuit, yeah, this exact same circuit also works as an integrator. If we analyze the circuit in the time domain, basically as a function of time, we can write V of t at the output is an integral of the input voltage, V in of t. If we analyze it in the frequency domain, meaning we are looking at frequencies and how the circuit responds to a frequency, then we say it works as a low pass filter. So in the time domain, and time and frequency are, well, I would like to say it's two sides of the same coin, right? Time is 1 over frequency, or frequency is 1 over time. So you analyze the circuit in the time domain, it's an integrator. And in the frequency domain, it's a low pass filter. And again, there's a derivation involved, and we can indeed derive that the output V out is 1 over R times C, an integral of the V in voltage. All right, about, let's see, 7 minutes remaining. So probably won't get to chapter 4, but high pass filter done. So coming back to the point that was made a little bit earlier, cascading, right? So what if we cascade these two filters together? Cascaded bandpass, right? Bandpass filter. First up, you have a low pass filter that's blocking all the frequencies above a certain point. Then you have a high pass filter that blocks all the frequencies below a certain point. So you have a band of frequencies in the middle that's allowed to pass through. So low pass filter plus high pass filter plus inverting amplifier to provide some gain. So the way it works is that every stage has a separate function. So if I was to plot this as a function of frequency, my V out. Low pass filter has characteristic, oh, that's not right. That looks like this, right? So that is my cutoff frequency or my break frequency. I'm going to call it F2 actually. So the second cutoff frequency should be higher. I mean, the low pass cutoff frequency should be higher than the high pass cutoff frequency. Otherwise, you would get a band reject filter. Instead of a band pass, you would get a band reject. And a high pass is like this, right? If F2 is higher than F1, you would get a U. Sorry, if F2 is lower than F1, you would get a U. So there's a band of frequencies in the middle that is being rejected. This is being passed, this is being passed, right? So F2 has to be higher than F1. So when you design it based on the values of RL and CL. Okay, RL and CL. And so if F2 is higher than F1, then you have a band pass filter. Pass block. Right? You can see that this is a low pass filter. So at the first stage, you have a low pass filter. All of these frequencies are allowed to pass through by the first stage. If you take the output here, you would have all the frequencies from 0 all the way to F2. And then the second stage is the high pass filter, which blocks these frequencies below F1, right? So below F1 is blocked, and then the rest at the output goes towards the inverting amplifier to provide the gain. We typically do not provide the gain in a cascade stage in the individual stages, because we do not want to amplify the unwanted signals, right? These signals we don't want, but they don't get blocked until the second stage. So there is no reason to amplify them right here. There's no reason to provide gain for those signals. And that's why the first two stages, low pass and high pass, are usually unity gain. So the gain is kept 1, and that's indicated by the same value for RL. So RL is the same, means the gain for the low pass filter is 1. The gain for the high pass filter will also come out to be 1. And that is a cascaded active band pass filter. Yes. Mark. Uh-huh.
How would you get like multiple and heat and multiple and
Like in terms of physical size, you mean?
well, like let's say like I want to have like a band pass with a lot of stuff.
Mhm.
Pass my stuff.
Well,
Protecting out the middle. And maybe I also want to reject out some really high end.
so what we are talking about is basically a graphic equalizer. Each graphic equalizer, if you well, you can, if you have one in your possession, you can actually take a look at it, or you can, just look up images on the internet. It'll have a specific frequency range for a graphic, well, actually I can bring it up right here. Each frequency range is there. It is its own band pass filter. So if we, let me bring up, see if I can find it. Anyway, we are at the end, so I'll come back to that question, but we're in end for chapter 3 finally. Let's see. So let's see, images. Now nowadays, of course, everything is digital and software, but let's look at this one. This is a professional 10-band equalizer. And if you take a look, it gives you the frequency right on top. So let me enlarge this a bit.
My friend actually has
The exact same one?
Yeah.
Wow. These are expensive, kind of, I think.
I don't know, maybe it's not an MSR one, but
Yeah. So you have the gain for each one individually. That's, of course, that's depending on the model, if they want to provide a separate gain. This is actually providing the actual filtering right here. Now, typically there should be a range, but if it says 31.25, that's, I'm assuming that's probably the mid range of that band. Okay. So I'm assuming this is probably the mid range of this band. And depending on you would have to dig into the spec sheet to actually look at and determine how narrow or wide the band is. Okay. But for now, I think I'm assuming that this is going to be the midpoint of that band. So in this case, again, how many band? 1, 2, 3, 4, 5. So 10 band graphic equalizer. And if you look at your, Windows PC, Mac OS, your smartphones, most applications will have a graphic equalizer in there. You can actually digitally just change it in the software. And they will also well, depending on the software itself, will have the frequency ranges on there. If you take a look at just, like a simple one, like a 3-band, we have bass, treble, and mid-range. The mid-range would be a band pass filter, and the bass and the treble would most likely be a low pass and a high pass filter, respectively. But you're doing the same thing. You're just changing the slider, and you're just changing how much gain you're giving to that frequency. And then this is for like overall gain.
What for is it?
Huh?
Where-
In the Windows, not manual, like in the Windows sound settings. All right, so we'll end class here today. We'll begin with chapter 4 on Friday. If you have any questions, well, send me an email, reach out to me in office hours.
Yeah, so how do you got that equation finally? That's where I got a little bit confused.